Howdy. So I received a comment on a video we did quite a while ago, the probability of making 50% on an option trade, which was based on another Monte Carlo type video where we simulated a stock's behavior, assuming that that returns were normally distributed. The commenter suggested that I kind of go through those calculations in detail, because what we ended up doing in an attempt to vectorize that, instead of just looping through to calculate all of these price changes, what we did is we came up with a fairly complicated matrix equation to do that. And I thought it was worth going over again because this is a point worth harping on, because these types of linear systems come up again and again and again. And so what I think I'm going to do is go through the code used to build that Monte Carlo simulation and then kind of build it, talk about it in a lot more detail, and then maybe as a follow-up turn to a physics question instead of a finance question and look at diffusion in a one-dimensional beam or something, where you have heat flowing from one side to the other, and look at the temperature distribution in terms of space and time. It turns out it's the same type of mathematics that we looked at in our Monte Carlo simulation, at least in terms of linear systems, in terms of being able to linearize and treat it as a matrix type system. So what I didn't go over in a lot of detail, let me switch over to a notebook, was what I meant by these systems of linear equations. So here we are. For now, we're just going to use Numpy. We'll add to our imports later. But in terms of linear systems, these types of things come up again and again, where you have three different, in this case, three different variables. In real world things, it's thousands, tens of thousands, millions, or more. In this case, it's just three, so it's x1, x2, x3, and they're all related to each other in a linear way. So how does this relate to a matrix manipulation? So let me get rid of my face here. Okay, so let me come here and I'm going to make this cell a markdown cell, and I'm going to write out a matrix equation and show that these two, what I write and this are effectively equivalent. So here is the same thing in matrix form. Now I brought up the Wikipedia article on matrix multiplication here. Basically, when you have two matrices that can be multiplied together, and again, not all matrices can be multiplied together, they have to be the right shape. To figure out the corresponding entry, and this kind of schematic does a very good job here. To figure out this entry in the product matrix, you'd multiply the corresponding row in the first matrix times the corresponding column in the second matrix. So in other words, this says that if I take this row in an element-wise way and multiply it times this column vector in an element-wise way, it should give me this entry here. In other words, the number 6. So 2 times x1 plus 3 times x2 minus 1 times x3 and is equal to 6. And that's basically what we have here. 2x1, oops, I forgot the plus sign here. Well, I'll put it in a second. Plus 3x2 minus 1x3 is equal to 0, or is equal to 6, I'm sorry. And you can see why I kind of spaced this out this way, because some of these entries are 0. Since the second equation has no x2, this entry here would be 0. So if we multiply this row here for 0 minus 1 times this column vector, we should get back this equation. So let me go back and just fix that typo here. So how do we solve this type of equation here? Well, if we had just like a single simple equation, let's just come down here and do y is equal to capital A times x. Let me make that a markdown cell. Oops. How would I solve this equation here? I mean, just in, I don't know what year you do the 7th grade, 6th grade algebra. You would divide both sides by a. So you get y over a is equal to a over a times x, but a over a is equal to 1. Anything divided by itself is obviously equal to 1. So is there an equivalent here to this matrix, which would correspond to a in this system, in this equation down here, that is akin to finding or dividing through or multiplying through by its inverse? So is there an equivalent of that operation, and what happens to this matrix when you multiply through by that? So let's delete this cell and shrink down this window. So let's bring it back to normal and just go, I don't know, there we go. So obviously, since I'm talking about it, there are equivalent concepts called the matrix inverse and what's also known as the identity matrix. So let me just talk about the identity matrix really quickly. So here's an example of a 3x3 identity matrix, and you can see it's all zeros except for this diagonal, which are all ones. And obviously this could be different sizes for different sized matrices. You could have 4x4, n by n, and generically. So what happens if we multiply this times a corresponding column vector? Explicitly, what is this equal to? Well, using our matrix multiply rules, we multiply this row element-wise times this column vector. So we get 1 times x is x, we get 0, and we get 0. So this first entry in this answer matrix, let me just write it out here. We get x, and you can tell what's going to happen. This next entry here below x is just going to be this multiplied by this column vector. So 0 is going to pick out the y, and then the z component here is going to be 0 times z, or just y. And likewise, this bottom one is going to be z. So our task is going to be to find a matrix which, multiplied by our matrix here, gives us back an identity. So if we were to multiply this equation by that matrix on both sides, so left and right, this matrix product should get back the identity matrix times our vector of unknowns, and that's going to be equal to our inverse matrix times this vector of knowns. And because the identity times the column vector is just the column vector, it basically gives us our answers. Now, fortunately, these things can be difficult to compute by hand, but fortunately, Numpy has a bunch of functions to do that for us. And let's just, before actually doing this, just let's show how to find the matrix inverse and show that it times a matrix is the identity. So I'm just going to set a random seed just for reproducibility purposes here, and I'm going to create a matrix A, and that's just going to be equal to mp.random.rand, and I'm going to make this matrix 4 by 4. Let me see if this works. Seems to. Let me just print this out. So let's go print our matrix is print A. So here's our matrix. Let's calculate its inverse. And the Numpy function to do that, well, let's just call it A inverse, is the Numpy function is np.linalg for linear algebra and inv for inverse. So that should calculate our inverse matrix. Let's print that out. Print inverse is equal to print A inverse. There we go. So what happens if we multiply this matrix times this matrix? So let's come down here. Print. We're going to use Numpy's matrix, it's matmul, matrix multiplication command, A inverse, and remember order is important here, times A. You can see that these are all essentially zeros off of the diagonal, and we have a bunch of ones along the diagonal. So our matrix capital X, which is what we're calling this guy here, is equal to np.array. It is equal to, oh, that's our unknowns. Never mind. We don't need that yet. That's what we're solving for. We want capital Y, which is this matrix here on the right-hand side. So that is equal to 6, 7, 1. 6, 7, 1. Excellent. So we calculate our A inverse. A inv is going to be equal to np.linalg.inverse of A. And if we multiply through, again, this becomes the identity matrix, which just becomes our vector of unknowns, and that is going to be equal to our inverse matrix times our what we called capital Y. So our capital X is going to be equal to numpy.matrix multiply A inverse, comma, capital Y. Uh-oh. Oh. Delete. Seems to run okay. So let's just print out our vector, our solution vector. So print x. So these should be our unknowns, and we could test that. Let's just take this first element here and let's just put it into this first equation here and see if we get 6. So I don't know, let's pull it out. Let's say lowercase x. Let's call it x1 just to be consistent with notation. That's going to be equal to capital X 0, the first element of that array. And let's just print out what is our equation here. It is 2 times x1. Well, actually, we'll need to pull out all of them, won't we? So let's just do x2 is equal to capital X1. x3 is equal to capital X2. Let's come down here and print 2 times x1 plus 3 times x2 minus x3. So 3 times x2 minus x3. And you can see we get 6. So you could do this for all of them, or equivalently you could say take your matrix A, multiply it times your solution vector, and it should give you back this vector here. So let's come down here and we'll just go print A. Oops, we're gonna have to do the matrix multiply command. np dot matrix multiply A comma x. 6 7 1 6 7 1. Outstanding. And for the sake of completeness, and this is what we'll probably do in as we move on, there is also a function called we'll just print out the answer. It's np dot lin alg, and it's called solve, and it just takes your A matrix and your matrix of knowns, and it should return your matrix of unknowns. So it's the equivalent thing that we just did. It's just it just saves a step of typing because it does it automatically for you. Okay, so that's all well and good, but how does this help us with the problem that we were talking about? We were looking to simulate stock behavior, and then we're also looking to solve what amounts to a partial differential equation, the diffusion heat equation. How does simple matrix manipulation and solving linear equations relate to those? Well, let's go back and kind of go back to our stock problem and write it out explicitly. Okay, so our stock simulation. Before I do this, I should mention about this matrix here. This thing is essentially all non-zeros. I mean, there are two zero elements, but essentially they're non-zero elements. And this is what's referred to as a dense matrix or a full matrix. And obviously, assuming you have a square matrix that's n by n, you're going to have n squared elements in that matrix. So if you have 1,000,000 by 1,000,000, you're going to have to store 10 to the 12th 10 to the 12th entries. And just in terms of memory alone, that's problematic. You know, it's prohibitive for almost all people. And also, to invert a matrix, generically speaking, it takes on the order of n cubed operations. So an n by n matrix, again, if it's a 1,000,000 by 1,000,000 matrix, now you're dealing with 10 to the 6th cubed. So you're dealing with 10 to the 18th operations. And again, that's pretty much a non-starter. But again, in most applications, you're going to find that almost all of these entries are 0, except maybe some along the diagonal or a couple other like off diagonal entries. And that's what's typically referred to as a sparse matrix. And obviously, you would need less matrix. You could just write your code in such a way that it realizes that if you don't specify a specific entry, it's a 0. So it saves a lot of memory. And also there are specialized algorithms that let you deal with these in a lot quicker, oftentimes a lot quicker manner, so that inverting them is not prohibitively computationally expensive. And you're going to see that for both the stock simulation and the when we get to the heat equation, the partial differential equation, we're going to end up with sparse matrices. And in the case of the partial differential equation, that's really going to bail us out, because the smallest matrix we'll have is 100 by 100 for a one-dimensional problem, and maybe 10,000 by 10,000 for two dimensionals. And again, dealing with those without the concept of sparse matrices would not be possible. So now let's move on to our stock simulation here. Okay, so this was our basic model here. The relationship between the stock price S on the ith day and the ith plus 1 day was given by this relationship here. So R is the risk-free rate, delta T is our time step, which we're going to take as 1 day, and then is equal to the square root of delta T times the volatility of the stock, and we're just going to make up a number and assume it's fixed over that period of time, times what I wrote as epsilon sub I, and epsilon is going to be a number sampled from the random normal distribution. You don't have to worry about that right now. We're just going to have a column vector of numbers. It's going to represent the that's going to contribute to the stock price change on a given day. So okay, so we can rewrite this like this. So the stock price on the ith plus 1 day is given by this. So if we know the stock price on the ith day, we could just kind of do an iteration and calculate the next day, and so on. So let's just kind of write that out, and just using a for loop. So I'm going to write, let's have 5 days worth of price information, or calculate 5 days worth of price information. And we're going to start off with an initial price. S0 is equal to, let's just call it S for now, not S0. So the price on the 0th day, I guess we'll call it, will be $100. And let's just make up a risk-free rate R of, let's just assume it's 1% annual, and we'll just divide it by 252 trading days per year. And I'm just straight lining this risk-free rate. Obviously, if you take this and run it out via a continual what's the word I'm looking for, compounded daily over these 252 days, you'll get a slightly different number, but I'm just going to be lazy and do it like this right now. So let's choose a volatility sigma of 0.3 annual, and we need to convert it to a daily number, so we're going to divide it by the square root of 252. We're going to need our epsilon, so epsilon is equal to np.random.normal, and we're going to set the size equal to the number of days, so n days. Just make sure that runs. There's a typo somewhere. Looks like I'm missing an equal sign here. So sigma is equal to that. Does that run? Excellent. So I'm just going to create a variable called stock data that's an empty list, and we're going to append our stock information to that list. So sdata.append. Good. So for I, let's do for I in range and days, S is equal to S times, what's our formula up here? R delta T, so we're going to need a delta T, let's just call it DT. DT is equal to 1.0, R times DT, plus what? Square root of dt. So np dot square root dt times sigma times epsilon sub I. Okay. What else do I need? Do I need to close? Just kind of offset this so it's a little easier to read. And let's also come up here and just set a random seed to a constant number. np dot random dot seed is equal to 2. Does this all run? Okay. s data dot append s. Where did I have it? There we go. dt. Come on. It's my MATLAB background kicking in. Square brackets in Python. Okay, so let's plot this out. plt.plot. I need to import the plotting library too, so let's just plot s data. Oops, what's going on? Oh, I know, this is the percent change, so we need to add that to the original stock price. There we go, that looks reasonable. So, okay, let me come up here, and I'm just going to copy this bottom equation here. So, copy. And I'm going to paste it down in a new cell down here, and I'm going to write out manually the first few iterations of this. So, paste. Oops. Okay. Okay, and to keep the notation simpler, I'm going to introduce this variable. I used the capital lambda in the last video, so I'll keep that in this one. So this is just equal to the terms in parentheses here. Again, it's just to simplify things. So it's going to be different for every day because of this epsilon sub I term. So we can have a lambda sub I, and that transforms that equation into this. So now let's just kind of write out a few iterations of this. Okay, so I've written them out and did a little bit of algebra to rearrange everything on all the kind of unknowns onto one side of the equation. So obviously the stock price on the 0th day is the stock price on the 0th day. That's our starting point. That should be self-evident. And then we kind of have each of these equations that relate the next day to the day previous to it. And you'll notice that these equations are all entirely linear. So this here is essentially the same thing that we had way up here. It's just a system of linear equations, and we should be able to write them out in a matrix form like this and solve it with our linear algebra packages. So what is that in matrix form? So in matrix form, it is equal to this ugly looking thing here. Stare at this for a while to convince yourself that it's the equivalent of this system of equations. Obviously, if we multiply this through, 1 times S0 is going to give us S0, and all these things are zeros, so it's not going to pick up these subsequent days. Lambda plus 1 times S0, that's going to be right up here, plus minus 1 times S1, that's going to give us which term here? That's going to give us this. And then the rest are going to be zeros, and so on. And now that it looks like I multiplied all these subsequent equations here from day 1 on by minus 1, just to keep the notation. I'm not quite sure why I did it that way, but it's equivalent. Okay. So the first thing you'll notice about this matrix is that it's sparse. You have either 1s or minus 1s on the diagonal, and then you're going to have some numbers on the diagonal that's right below that main diagonal. Everything else is 0. So we can take advantage of our sparse matrix libraries. So let's import those now. So let's come up here, and we'll do the import. So Scipy has a sparse library, and from that we're going to import a function called diags, which is going to help us build these kind of diagonal sparse matrices, and the linear algebra, which has the corresponding things to Numpy's inverse and solve functions. So let's just make sure those run to pull everything in, and we'll come down here and actually code things up. So I'm going to set that random seed again back to 2 just to keep all of our random numbers the same. So np.random.seed 2. So what I'm going to do is copy and paste from above all of our conditions here, and I'm going to define our lambda variable just so I don't have to keep typing all this stuff out every single time. So let's do that. Make sure it runs, make sure everything's good. Excellent. Now that diags command from the sparse library is analogous to another function that's in regular Numpy just called diag, and it allows us to build diagonal matrices. So suppose we wanted a matrix that was 5 by 5, zeros everywhere except for the main diagonal, and so we could, I don't know, let's say the entries on the main diagonal were 1, 2, 3, 4, 5. We could put in that array there, and we would put in 0 for our position, and it would create that matrix for us. And we can also do the same thing by, if we wanted to put these numbers on a diagonal right below the main diagonal, we would change that to -1. Well, now it's 6 by 6 because this is different sized, but we could put it on the +1. Oops. The 1, not the 11th, and so on. So that diags command from the sparse library does the same thing, except it returns a sparse matrix. So let me just delete this, and we will actually come up here, and let's build our sparse matrix. Now we need to provide a list of our diagonal arrays, or diagonal arrays. So our main diagonal is all -1s except for this first element. And since we're doing, where's our end days? Did I not copy that down here? Let's just do end days was equal to 5. Since we're doing 5 days and we have the 0th day, this matrix is a 6 by 6. So this diagonal is going to be 6 elements long, and it's going to be all -1s except for the first one. So let's just create a variable called ones, and that's going to be np.ones, and it's going to be size n days plus 1, and we're going to multiply it times -1. Let's just print that out, print ones. Okay, so now we want this first element to be +1. So let's just come back here, we'll put a semicolon in and go ones, the 0th element thereof is equal to 1. That looks good. So let's just get rid of this print statement, and now let's create this guy here, our lambda +1. So let us come down and go, I don't know what to call it, let's call it L, and we will call it that's equal to lambda +1. Does that run? Yes. Let's just print it out to make sure it makes sense. Print. Those numbers look reasonable. So let's build our sparse matrix M. So we want to call diags. Our list of diagonals. So let's just go L and ones. And where do these belong? Well, L belongs on the -1 row, and ones belong on the 0th row. And if we print this out, we'll see how it's actually stored in memory. So print M, and you'll see basically it just saves the coordinates of all the non-zero elements. There are functions to turn this into a regular matrix, to array, I believe it is. So if we wanted to see what it actually looked like or print it out, this is what it actually looks like. So we have 1 and -1s, and then we have our off, one below the diagonal. Another command that's useful for these types of things is the spy command. So plt.spy, it lets you kind of see a schematic of what the matrix looks like. So we can get a visual representation, because obviously for this 6 by 6 matrix it's not an issue, but if you had 1,000,000 by 1,000,000 you just couldn't print it out, and this would kind of give you a nice picture. Useful in debugging. So let's get rid of it because we don't need it. Okay, so now that we have this matrix, we need to create this matrix, this column vector here, And again, it's n plus 1, n days plus 1, so 6 days in our case. All zeros except for the initial stock price, which was, I called it S0 down here. So we'll create an array of all zeros and set the first element to S0. So let's call that, I don't know, let's call it capital Y, and that's np.zeros. And it's n days plus 1 long. And let's just change that first element n0 to S0. Print Y. Y. So here we go, 100, and then all of the others are zeros. So let's get rid of that. And now we're ready to solve the problem. So our stock price is going to be equal to SP solve, which is the sparse version. Did I not import it? linalg.sp solve. SP solve, which is the equivalent of the dense function in Numpy, just solve. And the arguments are the same. We pass in our matrix, we pass in our column vector, and that should be it. Does it actually run? Yes, it does. Let's plot out what S looks like. plt.plot S. And you should see this graph is identical to this graph. So let's actually, what did I call this? I called it S data, and this is S. So let's just come down here and say print S data, print S. So there's something a little fishy going on here. The plots look the same. Are these numbers the same? 1%, 1, 30%. Oh, 100% for the risk-free right up here. So 0.01. So let's run that, run that, run that, run that. And now we see that they're identical. 100, 99, 216, 99, 216. What's the last element over here? 94, 749, 94, 749. Okay, I think this is a good time to break and call it quits for part 1. I think in part 2 I will do the full Monte Carlo simulation, where we take this idea and we generalize it to a whole bunch of stock runs, and then in part 3 we'll look at the partial differential equation. Now this is what I did here is may seem a little bit like overkill, but when we actually do the PDE, you'll see how much more efficient in terms of time and computational resources doing this sparse matrix method is. So again, I'm going to split here and continue in part 2 in a bit.